Hello my champions, welcome back to KCET 2025 Masterstroke series, and as you know we are discussing all the chapters at one go, and today is the time for moving charges and magnetism. So if you are preparing for KCET 2025 exam, then definitely you have to subscribe to our Deeksha Karnataka YouTube channel and share this video with all of your friends so that they can complete their preparation absolutely of no cost. Now let's start with our chapter without any delay. I don't want to waste too much of your time. So first is definitely look into the list of important topics from the chapter. So all the important topics are basically, obviously, first thing is obvious, Lorentz force, very important concept. Then we have force on a current carrying conductor. Okay, then we have motion of a charged particle in a magnetic field. Okay, that is also super important. Then we have Biot-Savart's law, we have Ampere's law, we have Solenoid, we have Galvanometer and their conversions into ammeter and voltmeter. So this is a very important chapter. 4 questions on an average comes from this chapter. So all these concepts can get you those 4 marks. Now let's look into the first concept, that is Lorentz force. So Lorentz force is given by when a charge moves through a space having both magnetic and electric field, it experiences a force. Okay, so there is existing a magnetic field and an electric field. Okay, so suppose an electric field like this, a magnetic field like this, both exist, and some charge is moving some direction. Okay, charge is moving with velocity v. So they are all vector quantities, so we have to write vector with them. Now when they are all moving, okay, they experiences this particle, this charge particle q, it experiences basically a force. Now what is the force? The force for electric field, force under the electric field is very simple, that is q into E. Now what is the force under the magnetic field? Now under the magnetic field it is q into v cross b. Okay, q into v cross b is the magnetic force. Okay, sometimes this is also written as Fe, this is also written as Fb. Okay, and most of the cases this will be our main formula. In some cases we will use the combined formula, that is F equals to q into E plus v cross b. There are instances where they have given you values of E, V and B in I, J and K coordinates, and you have to do a lot of calculation to find the final force. That is also there, but most cases this formula is sufficient to calculate the force. Magnetic force is more important because the chapter is magnetism. Obviously we have covered electric force in our previous chapters, so that is why this is important, but this total form is also you cannot ignore that as well. Okay, this is called Lorentz force, obviously. Now let's move on to the next part. Based on this formula, a lot of small questions can come. We will solve some of them in our live session. Now force on a negative charge is opposite to that on the positive charge. So if a negative charge is experiencing, suppose I have a negative q, it experiences a force in this direction, then a positive q will experience a force in the opposite direction. Okay, so the expression in that, obviously there is a q, so if q is positive, it experiences a force in particular direction. If it is negative, it experiences in the opposite direction. So that has to be, you have to be careful about it. The vector product makes the force due to magnetic field vanish or become zero if velocity and magnetic field are parallel or anti-parallel. So if suppose there is a magnetic field like this and the object is moving in the parallel direction, then the magnetic force will be zero. Why? Because they are parallel or in anti-parallel direction. So if magnetic field and velocity are parallel or anti-parallel, Fb will be 0 because it is V cross B, right? So V cross B means it will be V sin theta, right? So force, magnetic force was V cross B, so Q Vb sin theta. So if sin theta is 0, then this magnetic force will definitely be 0. The magnetic force is 0 if charge is not moving, then velocity is obviously 0. Only a moving charge feels the magnetic force. If the charge is static, it does not feel any force. So if you are not studying, if you are saying okay, I will fail in the exam anyway, then you will not feel any pressure. Only if you are studying hard, you are trying to compete, then only you will feel pressure. So that is the same thing as you are trying to compete hard in your KCET exam. So charge is like that as well. Okay. Now let's move on to the next part, force on a current carrying conductor. Now assume that we have talked about individual single charge, right? Individual single charge experiencing some force. Now we have a conductor, okay, and this conductor is carrying some current. Okay, this conductor is carrying some current. There is a magnetic field present in the area. Okay, then this is the magnetic field. Okay, this is the direction of current, suppose. So what will be the force acting on this current carrying element? The current carrying element, it will experience a force, is called Bill sine theta. Okay, B is the magnetic field, I is current, L is the length through which the current is being passed, and sine theta obviously is the angle between the direction of current and the magnetic field. Okay, so L cross B, even though magnetic current is not a vector quantity, but L length is a vector quantity, and we take the direction of length in the direction of current. Okay, so we have some alternating arrangement. So force on a current carrying conductor is Bill sine theta. You can remember that Bill Clinton was American president, so that is how we used to remember, because during our time when I was a student, Bill Clinton was America's president, and like today nowadays Donald Trump is famous, back in the day Bill Clinton was also famous, so it was easy for us to remember the name, right? So Bill sine theta, it is sine theta obviously because it's a cross product. Now let's move on to the another part, motion of a charge in a magnetic field. Now a single charge is there and it is moving, we are back to single charge again, and it is moving in a magnetic field alone, no electric field is present. Now a charge moving in a magnetic field will experience a force, that is Lorentz force. This force acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. Now if there is no electric force, only magnetic force is present, then this force will be like a centripetal force. What is the meaning of centripetal force? Centripetal force, you remember when we discussed in our first few chapters that when you are rotating in a Ferris wheel or a circular motion, when you are in a circular motion, you experiences there has to be some force to for you to provide the continue the circular motion. That force is called centripetal force. Okay, centripetal force is a real force. Don't confuse with its ghost brother, centrifugal force. That is a pseudo force that does not exist in reality. It only experienced by objects in rotational reference frame. But centripetal force is a real force. Okay. So now if you see here, object is moving perpendicular, the charged particle is moving perpendicular to the direction of magnetic field. Cross represents magnetic field into the page of the paper. So cross, as I said, is a target, you can hit that cross, so that means it is into the page of the paper, and velocity is in perpendicular direction. So in that case it will experience the force that makes it to rotate in the circular motion. So there is a radius of this path, we will find the radius as well. If velocity has a component along B, this component remains unchanged, as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B as before, circular one, thereby producing a helical motion. Okay, so first of all, if this velocity is not exactly perpendicular, it has some component, say it has two components. Okay, it is at some angle with the magnetic field, then what will happen? So there will be a perpendicular component of the magnetic field, there will be a parallel component along with the magnetic field. Now this perpendicular component is like this. So perpendicular component will always try to make it move in the circular path. But if there is a perpendicular component, that will always try to make it move in the circular path. But this parallel component, it is not experiencing any force. So this parallel component will try to make it move in the forward direction uniformly. Okay, so this parallel component is taking it forward direction in uniform motion, and this perpendicular component is making it to move in a circular direction. So combining this is called helical motion. So it will move in a helical motion. So if theta is 90 degrees, there will be directly only circular motion. If theta is less than 90 degrees, then it will be there will be a value where it will be a helical motion. If theta is 0 degree, it will move in a straight line, no acceleration, nothing. Okay, so now radius of the circular path. Now let us find the radius of the circular path. When it is rotating in a helical circular motion, what is the radius? So radius will be r equals to mv divided by qb. Okay, or in more particular you can say mv perpendicular. If there is a perpendicular component, this will be mv by qb, that is the radius. Now angular frequency is given by, what is angular frequency? Angular frequency is qb by m. Okay, all the derivations are there in your book, you can check that out, but as I said, in KCET exam derivation is not important, so only you can start from here, that mv square by r, where v square is basically, mv square by r is basically your centripetal force, and qvv is the force acting on the charge, magnetic force acting on the charge. So from there you can calculate the radius. Now angular frequency omega is qb by m. Okay, the time taken for one revolution is time period is 2 pi by omega. So if you know 2 pi, you can put the values as well. So it will be 2 pi into m by qb. Okay, you can even calculate the frequency. So that is called sometimes frequency of rotation. The old name was cyclotron frequency. Cyclotron is no longer part of your syllabus, but frequency you can still calculate qb by 2 pi m. Okay, you can calculate. If you know angular frequency, you can calculate the frequency, you can calculate the time period, no matter. Okay, now let's move on to the another part, Biot-Savart's law. Okay, Biot-Savart's law is very, very important. Even though it is more like an application based question, in some cases maybe you will find questions from KCET coming from Biot-Savart's law, especially the concept of Biot-Savart's law, not super deep application of it. Some applications are already there in your syllabus. We have already applied it for circular current carrying coil, current carrying conductor, circular coil, then straight wire. So that is part of the syllabus curriculum. But in the KCET, what is important is understand the concept and the formulas wherever applicable. So we have I current is passing through this conductor. There is a small current element dl, and the angle that this current element is making with the radius vector is theta. Now this is the point where we are trying to find the magnetic field due to this current carrying wire. So first what we have done, in so far what we have done, we had a current carrying wire or a moving charge that is already moving in a pre-existing magnetic field, right? Now Biot-Savart law is talking about a charge is moving, and due to that moving charge there will be a magnetic field of that moving charge. So that we are trying to find here. Here instead of a single moving charge, we are considering a current carrying element. Okay, current carrying wire. So current carrying wire, and due to that current carrying wire is basically continuous flow of charged particles, right? So that continuous motion of charged particles, we are trying to find the magnetic field. And Biot-Savart, two friends, they said that the magnetic field at point P is basically proportional to the current that is flowing through the conductor. Next, it is proportional to the current element dl. And why we are saying current element? Because it does not necessarily to be a very perfect conductor. It can be a circle, it can be any curve, it can be a straight wire. If it is a straight wire, then does not matter. You can take it, you can easily integrate the factor dl and you can find the value. But taking small dls, because individual dls are, suppose I am taking a component here, that dl will be a different distance from this current element, right? So all all of the current components are at a different distance. So based on that, we have selected that it is dependent on this current element dl. Now what else? It is also proportional to the sine of the angle. If you combine all of the equations, you will get dBp equals to mu naught I dl sine theta by r square, and there is a mu naught by 4 pi, that is the constant, is always there. So this is the combined formula. And why this is dBp? Because this is due to a small element dl, right? Due to a small element dl, so that is why it is a differential dBp. To calculate the complete magnetic field, you have to do the integration of the entire length of the wire. So based on what shape, what size of the wire it is, this value of total magnetic field will vary. Okay, and here this mu naught by 4 pi is a constant, and in general it is 10 to the power of minus 7 Tesla meter per ampere. You have to remember 10 to the power of minus 7. Unit is not super important. As long as you are using all the other quantities involved, if they are converted into SI units, this 10 to the power of minus 7 is the only thing you need to remember. So mu naught is the permeability of free space. It is called permeability. Okay, and epsilon naught was permittivity, if you remember. Okay, one is vitamin, one is ability, right? Now magnetic field versus electric field, a small comparison. Both are long range and depends inversely on the square of the distance, right? Next is the principle of superposition applies to both fields. Okay, so both are long range and depends on inversely square of the distance, right? Long range means it works up to infinity, right? So both forces works up to infinity. There is an example of short range force. What is a short range force? For example, nuclear force is a short range force that works only very close to nucleons, okay, in the level of fermions, right? As you slowly go away, the force saturates and then it becomes zero. The principle of superposition applies to both fields. So if there are two fields acting on the same point, okay, then you can take the principle of superposition, that is a vector addition. You can vectorially add two fields, okay, and you can find the final field at that point. Next, what? The electrostatic field is produced by a scalar source. Very important for objective questions, MCQ, conceptual objective questions. So which of the field is produced by a scalar source? So scalar source means, for example, mass. Mass is a scalar quantity and mass produces gravitational field, right? So gravitational field is another example which is also produced by a scalar source. Okay, gravitational field and electric field, they are produced by scalar source. So basically electric field is produced by a charge, static charge, but magnetic field is produced by a moving charge, and in fact it is called a vector source because the source is ideal. Okay, so magnetic field can be produced by a moving charge or a vector source. Next is what? The electrostatic field is along the displacement vector joining the sources and the field point. The magnetic field is perpendicular to the plane containing the displacement vector and the current element ideal. So if you join the charge and the point of observation, you get the direction of electric field. Whereas in case of current element, magnetic field, it is basically perpendicular, so either into the page or towards the out of the page, right? If there is a current passing through it, we know that you have to apply the right hand rule, okay, right hand the thumb rule. So if you put it like this, so magnetic field is always perpendicular to the current element, right? So there is another difference. So they are in the same plane, same line, but in this case, in case of magnetic field, it is perpendicular, right? So how to do that? You put your fingers like this and then curl your finger. So if it is coming out of the page in this case, and when you are doing it for this part, it is going into the page. Okay, now let's move on. There is an angle dependence in the Biot-Savart's law, which is not present in the electrostatic case. Okay, so if you see that in electrostatic, it is basically Q into E, right? The force experienced nothing, no electric field. KQ by R square was the electric field. In case of magnetic field, there is a sine theta dependence which is absent in case of electric field, definitely. Okay, now let's look into this thing. So magnetic field due to a straight conductor. We have a straight conductor carrying current, say I, and we are trying to find magnetic field at some point P on the axis at some distance r from the conductor. Very long conductor is very long. Okay, from both sides. Then what is the magnetic field? The magnetic field is basically given by mu naught by 2 pi I by r square. Very careful in this case. It is 2 pi, not 4 pi. So that is why this formula you have to remember, I by r square, similar to that of the charge q by r square. Okay, here also I by r square. Only thing is, instead of having 4 pi in the constant, it is 2 pi. So that's where you have to be little careful about. Next is circular current loop. Here we are doing the entire circular current loop, including the dipole part. Okay, so what we are doing, we have a circular current carrying loop. Okay, and current passing through this is I, and then we take small element, right? We have done the derivation in our PU board classes, right? We are trying to find the magnetic field here. So magnetic field is basically given by mu naught I r square, and it is divided by 2 into x square plus r square to the power 3 by 2. So that is the common expression for magnetic field for on the axis at a distance say x from the center. Okay, and radius of the coil is r. Okay, if there are n number of turns, we generally multiply with an n over here, but we are right now we are assuming only one single coil. Okay, one single loop. In case you have to remember that in case you are calculating it for n number of turns, then you have to multiply this with n. Okay, that is a thing that you have to remember. In some KCET applications I have seen, they have given same formula but for a circular coil, not loop. Coil means multiple turns, loop means only one single turn. Right, now at the center of the coil, this x becomes 0. Okay, at the center of the coil x becomes 0, so you get that mu naught I by 2r. So that is the value of the magnetic field at the center. So yeah, as you can see, it is a constant value. It does not change with x. Obviously x is obviously cancelled, so this is a fixed value. Okay, now consider the second case. Now you are considering that the radius is very small. Radius is very small and the distance is very large. Now if you consider the second case where radius is small, distance is large, then what happens? So in that case, if you can approximate the below x square r square to be very small, okay, below r square to be very small, and you can ignore that r square completely, so you will get 2x cube, and then upper r square will be still there. Upper r square is not a smaller value, that means the overall value of the magnetic field will be obviously smaller, so you cannot ignore this r square. This is in multiplication, but this is in addition. So if it is in addition or subtraction, if the value of that quantity is low, we can ignore that, right? But if it is in multiplication, we cannot ignore that. If it is in multiplication or in division directly, we cannot ignore that. So here it was in addition, that's why we ignored it, but in this case it is in multiplication, that's why we cannot ignore the top one. Now what we can do, let us multiply pi on the numerator as well as in the denominator. Right, now what is the term pi r square? This pi r square basically represents the area of the coil, area of the loop, right? This is the area of the loop, so A. So let us represent it with A. So mu naught IA divided by 2 pi x cube. Okay, now you can write this as mu naught m divided by 2 pi x cube. What is m? M is called dipole moment of the coil. M is called dipole moment of the coil. It is I into A. So its dimension is ampere meter square. Sorry, unit is ampere meter square. Dimension is AL square. Okay, this is the dimension. So based on this, a lot of question I have seen coming in your KCET exam, and for standardization, what we have done mu naught by 4 pi, that is the constant value, into 2m by x cube. This is the similar to that of the axis of a dipole. If you remember, axis of a dipole was 2p by r cube, right? 2p by r cube, mu naught 1 by 4 pi epsilon naught. Similar to that, you can compare this, you can remember it just like the dipole. If it is on the axis, you can simply use this formula. Okay, now any other direction, it is not there in your syllabus, so you can simply remember this. It is on the axis of the circular current carrying loop. The magnetic field is given by mu naught by 4 pi 2m by r cube. Now let's move on. Ampere circuital law, another easy thing, that we have a current carrying wire. Any wire, does not necessary, and if we have a closed loop, if we consider a closed loop around it, and the magnetic field at any point is B, and then the current element at this point is dl, okay, then it is given by the magnetic field around a closed loop depends only on the current, electric current passing through the loop. Okay, that is, in other words, if you remember Gauss's law, there we said charge enclosed by the surface, here current enclosed by a loop. Okay, in that case it was a three-dimensional surface. In this case it is a two-dimensional loop. It can be a circular loop, it can be a square loop, it does not matter what is the shape of the loop, as long as it is a closed loop and as long as it is having some current passing through it, Ampere circuital law is applicable, and that is B dot dl equals to mu naught I. Okay, based on that some questions have come. We will solve in our live class as usual. Now let's see this question. So two identical current carrying coaxial loops. So we have one loop like this, another loop is like this, and what is said that in opposite they are carrying current, equal current in opposite direction. So one is carrying current in this direction, say I, another one is carrying current in this direction, say I. Now what is the thing, that a simple Amperian loop passes through the both of them at once, calling the loop C. So there is an Amperian loop which is passing through both of them, and let's name this loop as C. Okay, so this is the loop 1, this is the loop 2, and Amperian loop is basically passing through both of them. Now B dot dl is equal to plus minus mu I. The value of B dot dl is independent of the sense of C. There may be a point on C where B and dl are perpendicular. Next, B vanishes everywhere in C. Now if you see that this, what is the total current enclosed? It says I naught I enclosed. So in this case B dot dl is basically this formula, right? So mu naught is given, I is plus I plus minus I. So if you consider this as plus I, this will be minus I. So total current enclosed will be equals to 0. So total current enclosed 0 means B is 0 everywhere along the C. Okay, as simple as that. If there are two coils carrying current, if you consider an Amperian loop, you will find the magnetic field is 0. Now let's move on to the solenoid. Now magnetic field due to a solenoid is given by mu naught Ni. Very important formula, but simple yet important formula to remember. Why so? Because mu naught Ni, based on this a lot of questions generally come in your exam, so that's why mu naught Ni is important. Here N is the number of turns per unit length, so it is not the total number of turns, it is number of turns per unit length. So they will give you, there are 2000 turns in a solenoid of length 2 meter. Okay, so in that case this is the capital N and this is length. So number of turns will be per unit length will be, you have to divide this 2000 by 2, that is 1000. So this is an important step that you have to remember here. Even though the formula is simple, the questions, that the only trick that comes from this type of question is that they will give you total number of turns and total length. You have to find it for unit length, that is important. Now inside a solenoid the magnetic field is always constant, that is very property of solenoid. Okay, center of the solenoid, except at the edges. Okay, except at the edges, everywhere in the solenoid magnetic field will be constant. And if you just simply increase the length of the solenoid keeping the small n same, magnetic field will not change. Okay, so magnetic field depends only on capital I and number of turns per unit length. If you keep the number of turns per unit length same, but you have doubled the length, current is still flowing the same, then the magnetic field will not change. So this type of objective questions are very common in your KCET exam. Now let's move on to the next part of our part, that is force between two parallel currents. Okay, so we have two parallel current wires. Actually I have combined two different cases in one diagram that will help you to understand how they work. So we have two currents. First of all, let us consider, do not consider this wire first. We have two wires, they are carrying current in some direction. So in this case, the force acting between these two current carrying wires will be attractive in nature, whereas the force acting between wires carrying current in the opposite direction, that will be repulsive in nature. So if current is being carried in the same direction, they will be say, as you can see, this is into the paper, this is out of the paper, so they will attract each other, and in this case both are out of the paper, so they will repel each other, right? So this is the basic fundamental thing that you have to remember for objective questions. Parallel currents, same direction repel, opposite direction attract. Same direction attract, opposite direction repel. So and the force between them is basically given by mu naught n Ia Ib by d into L. L is the length of the wire that you have to consider. Now let's move on, that this force between two wires. So if you consider the force of say this is wire number 1 and this is F12, and if this is wire number 2 and this is F21, then you can say that these two forces are actually equal and opposite in direction. Always maybe parallel or anti-parallel, it is always opposite direction. Okay, so that is why it is written as a negative sign, right? Now let's move on. The ampere. So from here you can define ampere. The definition itself is not super important, but the concepts that coming from this part is important. That how can you define ampere? When two very long straight wires, straight parallel current carrying wires, each of negligible cross section, that means very very thin, okay, are and placed 1 meter apart. So the distance between them is basically 1 meter, and would produce on each other of these conductors a force equal to 2 into 10 to the power of minus 7 newtons per meter of length. So this is very very important, per meter of length, 2 into 10 to the power of minus 7 newtons. So the value you have to remember. Based on that some questions might come, so this is a important thing to remember. Now let's look into the torque on a rectangular current carrying loop. So if you consider a current carrying loop like this and it is kept in a magnetic field, then it will experience a torque. Okay, so one arm will experience a force upward direction, another arm will experience a force in the downward direction, so that will make this to rotate. Okay, that is the basic principle of a motor. Okay, so if you are sending current through a coil and that coil is situated in a magnetic field, that helps the coil to rotate. So based on this motor principle, all the motors are basically one or another derivative of this same principle. So starting from your fan, okay, starting from fan or rotary motors where you pump the water, that is also based on this simple point. And the torque formula is IAB. Okay, for n number of turns it is given by NAIAB. So I used to remember it by NAIAB. Okay, the magnetic moment of a single loop is defined as M is equal to I into A. So IA, you can say that this is basically torque. So for n number of turns the formula is magnetic moment is NIA, and the torque is basically M cross B. Very very important formula. So it is MB sin theta. So based on the theta angle theta, the torque magnitude also varies whenever you are considering this magnetic loop, right? So there are a few questions on this as well. Now let's move on to the next part, moving coil galvanometer. If you see moving coil galvanometer, okay, the same thing here. We are sending current in a already existing magnetic field, and the torque that is experienced, that is balanced by using a spring. Okay, there is a spring having some fixed spring constant. That spring balances the torque that it experiences. Okay, and how much torque it experiences, based on that it gives different deflection. More the torque, more extension is required from the spring. Okay, and based on that you get different reading. The angle of deflection is basically is proportional to current. So how much deflection is happening in the galvanometer depends on the current obviously, and here phi is called the angle of deflection. This is a galvanometer constant. It is given by NAB by K. Okay, the values will be given to you in case K is the spring constant, N is number of turns in the galvanometer coil, A is area, B is already existing magnetic field. So based on this formula, maybe one question might come. Okay, so you don't know what question will come, so you have to remember this equation as well. Simple equation, not super difficult. Now we already have learned this in our class, right, in our theory class, that an ideal ammeter should always have zero resistance. In practical ammeters, the resistance is kept as low as possible. To convert a galvanometer into an ammeter, we need to connect a shunt, that is a small value resistance, in parallel to the galvanometer. Okay, so most of the current is passing through the resistance and very small amount of current is passing through the galvanometer. The current sensitivity of an ammeter is basically given by phi by I, so it will be NAB by K. So the same formula that we have learned, the galvanometer constant, so current sensitivity is exactly equals to the galvanometer constant. Okay, so this is how you can convert galvanometer into ammeter. Now let's look into the next part, galvanometer into voltmeter. So an ideal galvanometer should have infinite resistance. In practical ammeters, the resistance is kept as high as possible. To convert a galvanometer into a voltmeter, we need to connect a high value resistance in series to the galvanometer. This voltage sensitivity is given by phi by V, and that can be given by NAB by RK. R is the resistance that you apply. Okay, because it's a high value, you can ignore RG, only R is sufficient. So this is the voltage sensitivity. Okay, now let's move on to a problem. Let's solve it. A galvanometer of resistance 50 ohm is connected to a battery of 3 volt along with the resistance of 2950 ohm in series. Full deflection of 30 divisions is obtained on the galvanometer. In order to reduce this deflection to 20 divisions, the resistance in the series should be. So we have a galvanometer and we have a resistance of 2950. The resistance of the galvanometer is 50 ohm. Okay, suppose there is a current passing through this galvanometer is I, suppose. Okay, now what is the voltage drop across this? What is the voltage drop? How to calculate the voltage drop? Obviously current is given, means we can calculate the voltage drop. Okay, V is equal to IR. Okay, now what is R here? So galvanometer and this resistance are in series, so you just need to add them. I into so this is R1, it will be 50 plus 2950, definitely it will be 3000. We can smell that from the given question. So 3000 I is the current through the galvanometer, into R, I is the voltage across the galvanometer, right? Now this is giving us a 30 scale deflection. So 30 scale deflection means while solving this problem, you can say that this is basically equivalent to say 30 volt. There will be a constant. I am taking that constant to be 1. So 30 equals to 3000 I. So what is the I? So I will be equals to 30,000, 30 divided by 30,000. Now this is the galvanometer current, right? So the galvanometer current is always constant, the maximum current that can pass through the galvanometer, right? So 1 by 100 is constant value, maximum current through the galvanometer. Now what we are trying to do, we are trying to increase the R so that this voltage is is decreased to 20. Okay, so what we have to do, what we can do, we can change the voltage to 20. Okay, for the same current. Okay, the same current, so we are using the same current, that is we are trying to reduce that 30 reading to 20 now. So what will be the value? Current is same, that is 1 by 100. What is the resistance? Okay, no, I think this is a wrong approach. So what is given here? Let's see the question. Galvanometer G in series with the resistance 2950 and the voltage of the battery itself is given. Okay, so we don't need to wait too much. So what we have to do, you have to calculate the current directly. So current we can calculate directly. So this is 50. So as we know that V is equal to IR, so 3 is equal to I into R. R is 29. 50 plus 50, that is I will be equals to 3 divided by 3000, that is 1 by 1000 or 1 milliampere. I am just writing 1 by 1000, that is the current here. So in this case the galvanometer is showing you a deflection of 30 scale. Okay, so when the current is 1 by 1000, when the current is 1 by 1000, it shows a deflection of 30. Okay, so 30 deflection is shown for current 1 by 1000. So how can we get 20 deflection? To get 20 deflection, we have to reduce the current, that is 20 by 30 into 1000, 1 by 1000. This should be the current. We have to control the current to reduce the deflection of the galvanometer. So this is now the new current. So voltage is same. Voltage is same in this case. Instead of current, voltage is same. That is 3. Now 2 divided by 3 into 1 by 1000. This is the current, new current, into R. R is basically R1 plus 50. So let's say the new resistance is R1. So that R1 plus 50 should be equals to, should satisfy this equation. Now do the multiplication. R plus 50 should be equals to 3000 into 3 divided by 2. So it will be 1500. That is, you will get 4500. Okay, 4500, and the new resistance will be 4450 ohm. So this is the new resistance. So correct answer is option C. So with this I will conclude this session and I will be back live tomorrow. So wait for me at 11 AM. Till then, bye.